Assalamu alaikum, dear friends. Welcome to the lecture of the quantum mechanics. In this lecture, we will discuss about the discrete spectrum and continuous spectrum. What for what states we have a discrete spectrum, and for what state we have a continuum spectra, and what is special about discrete and continuous spectra. So the first is discrete spectrum. Discrete spectrum is just like, consider that if we obtain some set of energy values, so these are the energies value. So these are E1, E2, E3, E4 will be separated by well-defined boundaries. Mean we can differentiate between the range of E1, E2, E3, and E4. So these set of energy will be known as discrete spectrum, and this exists for bound states. And what are the bound states? Bound states are those states for which the particle is bounded between the two potential. Mean, for example, this we have all this, and here potential is infinite, and here we have also potential. So particles cannot go out of this potential. So this is the bounded particle can exist or reside between these particle cannot go out of this potential. For this we will have some discrete energy levels, E1, E2, E3, and E4. So discrete spectrum is the set of energy values which have a well-defined values and can be distinguished from one another. E1, E2, E3, E4. Just consider like it that we have in, for example, in nucleus, and we go up. We have first electronic state, second electronic, third, and as we are close to the nucleus, so particle will be bound here. Particle will be bounded to the nucleus potential. So these we will have a discrete spectrum here. E1 and E2 will be can be distinguished from each other. As we go up to higher energy levels, as we go up to the higher levels, so we can, that the hold of the nucleus on these electrons will be decreasing as we go up. So the hold of the nucleus will be decreasing. So these states or these levels will become continuous to each other. Okay. So here bound state occur when the particles cannot move to infinity. Bound state means the particle cannot go to infinity. Particle will bounded between the two boundaries, and that is the particle in confined or bound at all energy to move within finite and limited region. Mean our particle will be limited to particular some regions, and which is delimited by two classical turning point. Mean particle cannot go out of that points. I have, as I would describe drawn here, x1 and x2 particle cannot go out of this. The particle is limited. Particle motion is limited between these 2 points. The Schrodinger equation, when we apply Schrodinger equation, and this will give the equation of motion for it, and also gives allowed values of energy, and we will apply for the different cases later. So the infinite square well potentials and the harmonic oscillator, these are the example of the bound states. Infinite square well potential with particle is bounded between the two states, like here we have two walls, v of minus infinity and v of minus plus infinity. So the particle is bound infinite square well potential, and harmonic oscillator in which particles is bounded between the two potential, and particle cannot go outside from that. In this if I center it so that we can see it, discuss it clearly. In the potential of figure 4.1, we have this potential for the discussion general. The motion of the particle is bounded between the classical turning point x1 and x2 when the particles energy lie between v minimum and v1. You can see that this is actually a graph between the potential and distance. On the x-axis we have take the x displacement, and the y-axis we have took the potential. As we go up, the potential will increase. But as if we look for graph, this is the potential v1, and this is the potential V2. So our particle is bounded by these two potential V1, no sorry, this V minimum, this V minimum and V1. So this part, our particle cannot go out of this potential, and its potential and this is V1, this is V2, and this is the minimum value of the potential. In this V minimum, you can see that V minimum is the minimum value of the potential, and this V minimum is less than E. You can see that from the graph, this V minimum is the less as compared to this E values, and which is also less than V1. You can set the range of potential and then apply our equation of motion to find its different state. So in this, just in short, we can say that the power particle is bounded between the V minimums and V2. Particles cannot go out of this region, and in this case, their spectrum will be discrete. If we find the different values of energies, so it will give us a discrete, mean there will be well defined boundaries for each energies. Next slides. The state corresponding to this energy range are called bound state. Mean we are discussed in the above. This state will be bound state when the particle is bounded. These are defined whose wave function are zero. Mean when our particle is bounded between 2 points, so potential at that potential will be zero at x plus minus zero potential. Our wave function will be zero at that. Mean particles here our when at this point our wave function will be zero, because there is no probability of finding the particles away from, out of these boundaries. Particle can reside inside, so this there will be some value of wave function in the boundaries. If we have wave function, so definitely there will be probability psi and psi steric, which is the probability of finding the particle between two states. So particle cannot come out this. Usually the bound state have energy smaller than E1. Okay, and if regarding this we have a theorem for example in a one-dimensional problem, the energy level of bound state system are discrete. When we have bound state, so the mean like I discussed the nucleus example, so our when we have bound state, particle is bounded, so we will have discrete energy level which are very sharp separated from this. And non-degenerate means we will not have the value of those states for which energy will be same. So each level, each state will have a different energy, and no states will be can be found with the same energy. Each state will have a different energy. And next is continuous spectra. Under what condition we will have a continuous spectra? For the unbound state, in this particle will not be bound. Particle can go out. Unbound state occur in those cases where the motion of the system is not confined. A typical example is free particle. When we have free particle, so particle can go anywhere. For the potential displays in the figure, there are two energy range where the particle's motion is infinite. The first was V1 to V2 and again E to greater to V2. In the case when particle is bounded between V1 and V2, you can see again to that graph. This was a graph where particle is bounded between V1 and E1, V1 this one, and similarly a particle here at V2. So V1 is less than V2 when the particle is between E1 and V2. In this case, the particle motion is infinite only toward at x is equal to minus infinity. That is, the particle can move between x is equal to 3 and x is minus infinity. Classical turning point. So particle cannot go out that, and energy is spectrum will be continuous. If we particle go out, mean and none of energy will be degenerate energy. And the second is for E greater than V2, when particles go out, the energy spectrum is continuous and the particle motion in infinite in both direction. Means if particles goes to plus infinity, so our potential or x goes to minus infinity, our wave function will not goes to zero. There will be some probability of finding particle. For example, if we have no wall, so particle can be found anywhere out of the wall, and we will have some set of energies, and spectrum for this will be just like continuous. To see this, let's we will have we will if we write to find if we try to write the solution for Schrodinger equation, so it will be sum of all the possibility, sum of all the probability, means a1 psi 1, similarly a2 psi 2, and so on. So if we take the probabilities of these separate terms, so this probability should be equal to the sum of one sum of whole term probability will be equal to this one term. Okay. So example for the next is mixed spectra, when where we have particle uh, where we have the case when the mixed spectra and continuous spectra and discrete spectra both exist. Where the particle is bounded in some regions, we will have discrete spectra, and where the particle is unbounded, we will have a continuous spectra, continuous range of energy. So if we have two discrete spectra, particle is bounded at some point and not bounded at other point, so we will have both discrete spectra as well as continuous spectra. So such spectrum are called mixed spectra, when we have continuous spectra and discrete spectra. So potential that can find the particle for some energy give rise to mixed spectra. Mean we have a discrete spectra as well as continuous, because at some point particle is bounded and at other point particle is not bounded. So the motion of the particle for such potential is confined for some energies values, and for other it is not. So for instance, if the potential displayed in figure, mean the particle, for example, V minimum to V1 is confined, and E greater than E, if the particle has energy E greater than V, so particle is not confined. So we have a continuous spectra for unbound state and a discrete spectra for a bound state. Such example of such spectra are in finite square well potential, and the coulombs or molecular potential are the example of a mixed spectra, where we have both type of spectra. So I will stop at this point and inshallah discuss in the next lectures.